Okay, now that we're done with the delta well, we can talk about the finite potential well, which in many ways is sort of just a extension of the delta well. Because if we look at a potential that looks something like v of x is equal to, say, negative v naught, which is a constant between negative a and positive a, and it equals 0 everywhere else, so when the magnitude of x is greater than a, what this looks like is it's just a well, as the name would put it. Let's draw it in red. So let's say this is x equals negative a. Whoops. Now let's say that this is x equals positive a. Then our well looks something like this, where this is y equals negative v naught. So in this case, compare it to like a delta well, which is basically just an infinitely deep, infinitely narrow, finite. Like it's a delta well looks something like this. So for all intents and purposes, it's kind of the same thing. The only difference is that instead of being finite and shallow, it's infinitely narrow and infinitely deep. So sort of everything that we learned when doing the delta well sort of applies to this as well. So if we wanted to actually solve for the wave function here, we would do it in 3 parts. So first off, when x is less than negative a. Second, when x is between negative a and positive a, and then finally when x is greater than a. So we solve it in these 3 regions, then we stitch them together using the same boundary conditions we've enforced all this time before. So let's start with, obviously, this sort of admits both bound and scattered states, depending on whether the energy is positive or negative. Let's start with bound states. So bound states. And let's start with part A, which is when x is less than negative a. So to the left of it, the potential is obviously always going to be equal to 0. So our Schrodinger equation reduces to negative h bar squared over 2m times the second derivative of psi with respect to x squared. And this is equal to the energy multiplied by psi. And alternatively, if we want to rearrange this, then we can say that d2 psi by dx squared is equal to negative 2me over h bar squared times psi, or alternatively, as we've done so many times before, we redefine this as k squared times psi, where k is a constant that's defined as the square root of negative 2me divided by h bar, and I suppose it's not a constant because e here will change, but anyway, this is sort of the same system as the delta well, and it has a general solution that takes the form of exponentials. So we've already solved this many times before. The solution is just psi of x is equal to some constant a times e to the positive kx plus some constant times b times e to the, actually I think the actual notation is like ae to the negative kx plus be to the positive kx, and this is when x is less than negative a. And once again, we sort of impose conditions here because remember that x goes down to negative infinity. And if x goes down to negative infinity, if a is non-zero, then this exponential here, negative k times negative infinity, is going to go to k, is just going to become positive infinity. So this term blows up as x goes more and more negative. So by necessity, we require that a equals 0. So as a result, the actual solution is psi of x equals be to the positive of kx when x goes from negative a to negative infinity. Okay, next we have the inside of the well, so from x equals negative a to positive a, so part B, between negative a and positive a, and here we actually do have a finite potential now, so it's going to be negative h bar squared over 2m d2 psi by dx squared, this time subtracted by v naught times psi, because remember this is plus v of x times psi, so v of x equals negative v naught, and then this equals e times psi. So once again, we're trying to solve for psi, so we want to isolate the second derivative. So we're going to start by saying, okay, negative h bar squared over 2m d2 psi by dx squared, and we're going to move the v naught to the other side. This gives us e plus v naught multiplied by psi. And then finally, we move all of the constants out, so d2 psi by dx squared is equal to negative 2m e plus v naught over h bar squared multiplied by psi. And alternatively, here, so we do the same thing as before where we define it as k, or in this case a different constant, let's call it L, but it's a little bit different here because we're going to, instead of this, we're going to write this as negative L squared times psi. And the reason why we're doing this is because if we look at L, L is equal to square root of 2m E plus V naught over h bar squared. The problem here is that E is negative and V naught is positive, because the well is at negative V naught here. So what we're happening is that it's E plus V naught. So V naught is positive, E is some negative constant, which is the negative energy. 2m and h bar squared are all positive. So this term here, the problem is that the energy is always negative, but it can never become more negative than the minimum of the well. So what we're saying is that the magnitude, this is something we've proved before in an earlier problem, but basically the magnitude of the energy has to be less than the minimum potential in the well, which in this case is V naught, because the minimum potential is everywhere here. It's just a flat V naught line. So the magnitude of E has to be less than V naught. So what that means is that even though E is always negative, this interior term always has to be positive no matter what. And because of that, it's not allowed for us to include the negative inside the square root like we were able to do here. So as a result of that, we define it as negative L squared times psi instead of just L squared times psi and absorbing the negative into the square root like we did for the complex, or not for the complex, but for the exponential solutions. So this seems to apply, it seems to imply that we should have complex exponential solutions, but if you think back to an earlier section when we were introducing sort of the difference between just standard sinusoid solutions and sort of complex exponentials, hopefully you remember that complex exponentials are specifically reserved for scattering states, whereas for bound states like this, where we still have the same setup, there's actually two ways to write this. One way is the complex exponential general formula, which is used for scattering states. The alternate is the sinusoid solutions, which are used for bound states, which is exactly what we're going to use here. So the general solution for this can be written in two ways. We're going to write it in the way that we do for bound solutions, which is as a sinusoid. So psi of x is actually equal to c times sine of Lx plus d times cosine of Lx. And once again, the reason why we're doing this is because traditionally we write complex exponentials for boundary states, or for scattering states, and we write sinusoids, just real normal sinusoids, for bound states. So this is the general solution between negative a and positive a. There's no term here that blows up to infinity as we go to extreme values of x, either positive or negative infinity, so we can't get rid of either of these constants. This just remains as is. Finally, in part C, which is when x is greater than a, we have sort of the exact same solution. So it's v is equal to 0 again. Everything works out the exact same way. We're going to get an exponential solution again. Psi of x is just going to equal e times e to the negative kx plus f e to the positive kx. And once again, this is when x is greater than a. So here we have the same sort of setup where since x is going to positive infinity, what's going to happen is that this term is going to blow up to infinitely large values, and we can't have that if we want psi to be normalized. So as a result, we sort of just require f to equal 0. So as a result, the actual solution is psi of x equals e times e to the negative kx, with x being greater than a. And with that, we have our piecewise solution for psi, with it being a complex, with it being an exponential function to the left and right of the well, and inside the well, it ends up equaling like sort of a sinusoid, c sine Lx plus d cosine Lx. And technically, we've solved it. This is the solution. The next part is just all about enforcing boundary conditions and getting everything to equal, or effectively getting all of these coefficients to equal each other. And then after that, we'll really be done. Okay, so now we have our bound state wave function as a piecewise. The next thing that we would do is we would enforce sort of the continuity requirements as we've done before, and then we do all that and we would finish technically solving this. Now, the thing is, psi and d psi by dx at this time are both continuous instead of only psi being continuous. And the reason for that is because the potential here is always finite. There's no infinite point like in the delta well. And because it's well behaved, we can actually simplify our work a little bit and make this a little bit easier for us. And what I mean by that is that if you look back to problem 2.1, in that problem, we were asked to prove a bunch of theorems. And one of the theorems we proved is that if the potential v of x is even, then the wave function psi of x is either even or odd. And this makes things a little bit easier, because if it's even or odd, regardless of which one it was, it effectively means we can mirror what psi of x looks like at x equals 0 across from the negative and positive side. So what that means is that instead of having to impose boundary conditions at x equals negative a and x equals positive a, and you know what, I just realized I made a mistake here. This is x less than negative a, my apologies. And anyway, instead of having to enforce these boundary conditions at two different points, we can just look at one point and then just mirror everything onto the other side. So there's actually, we can rewrite this. So there's two cases. Psi of x is either even or psi of x is odd. So let's suppose that psi of x is even. Then what that means is that the piecewise is going to change a little bit. It's going to equal, so at the top, this is still e times e to the negative kx. In this region, in the middle region, if psi of x has to be even, because psi of x is either even or it's odd. So if it's even, sine is an odd term, cosine is an even term. By definition, c has to equal 0 as a result of that. Because if c wasn't 0, c sine of Lx plus d cosine Lx isn't even or odd. It's just it's a waveform. It's not even, it's not odd. Or it could possibly be even or odd with very specific constants, but generally it's not even or odd. So by requirement, c has to equal 0 in the case that psi of x is even. So this is just going to equal d cosine Lx. And we're sort of only considering this, so this is when x is greater than a, this is when x is between negative a, and this time, instead of being between negative a and positive a, or you know what, actually, this is not quite right. Instead of being between negative a and positive a, instead we can make it just between 0 and positive a. So x is greater than 0, x is less than positive a. And what this is doing is basically I'm enforcing the fact that I don't have to care about what x looks like when it's negative. I only have to look at its positive side, because since it's even, it's just going to like mirror itself across the x equals 0 point anyway. So I can just define the right side, or the negative side, or the left side, I suppose, as psi of negative x. And this is when x is less than 0. So what this part is because for an even function, psi of negative x is just equal to psi of x. So because of that, this is just going to mirror itself onto the other side. So as long as we know what it looks like on one side, we can just copy everything we see on the other side. So this is a more convenient thing to solve compared to this term, because we're getting rid of one of the sinusoids. Same thing, alternatively, if psi of x is odd, then psi of x is equal to, and same thing as before, so we have e times e to the negative kx when x is greater than a. And then in this case, for the opposite reason, since psi of x has to be odd now, the d term has to equal 0 because cosine is even. So instead we have c sine Lx when x is between 0 and positive a. And then we have psi of negative x, which is just when x is less than 0. And in this case, psi of negative x is equal to negative psi of x. So we do the same mirroring technique, but we just invert everything for the odd case. And what we can do is we can just solve these two systems separately. And doing two easy systems is a lot better than doing one slightly more complicated one, because a lot of times these systems that you add on extra terms tend to get exponentially more complicated. So because of that, it's always preferable to just degrade something into two simpler things and do those two cases sort of separately, piece by piece. Okay, so far we've sort of enforced that psi of x is either even or odd, and these are two equally valid piecewise functions that we can work with. It turns out that a lot of the later problems deal with the hypothetical case where psi is odd, and has us solve everything we're going to solve here for the case where psi is odd. So we're going to just focus on the even case, and really the method for solving this resulting system is kind of analogous regardless of which one you use, because the only thing that differs is whether or not this is a cosine Lx or a sine Lx. And since they're both really trigonometric terms, the way of solving them is kind of mostly the same. So let's look at the case where it's even first. Or let's just look at the case where it's even and ignore the odd case for now until we actually get to the problems in the back of the text. At this point, to solve this, we just enforce continuity of psi and its derivative. So continuity of psi and d psi by dx. So we have at x equals positive a, because remember, we don't have to worry about negative a now since we've enforced that this is either even or odd. Then we have e times e to the negative ka is equal to d cosine times la. And then we take the derivative of this, so negative k e times e to the negative ka is equal to negative l d sine of la. And at this point, I have two equations, two variables. This is very easy for me to just substitute everything. So I can divide the bottom term by the top term. So negative k e to the negative ka divided by e times e to the negative ka is going to equal negative l d sine of la divided by d cosine of la. And at this point, it's just a matter of canceling things out. This is going to give me negative k e to the negative ka, or not even that, the exponential also cancels out. So just negative k is equal to negative l times tangent of la. Cancel out the negatives, we have k is equal to l tangent of la. Now, this is just a direct relation to energy. Technically, we've solved everything already, because k and l are both directly functions of energy. We know that k is equal to square root of negative 2me divided by h bar. And we know that L is equal to the square root of 2m e plus v naught divided by h bar. And what the problem here is that even though we've technically solved this, this is not a very nice function. If we actually wanted to find what the energy was, this is a very mean function to work with, because these are two different variables, k and l, that both have their own implicit dependence on e in different ways, and also the fact that there is an L term in this tangent, which makes everything even harder. This is a transcendental. It's not possible to be solved algebraically. You have to plug it into a computer. And it's very inconvenient to use something like this because it's two different variables and they both have implicit sort of dependencies on e. So what we can do to sort of make this a little bit easier on ourselves is we can try to redefine everything using substitution into a single variable. And that is exactly what Griffiths does. So we're going to follow along here. I personally feel like some of the steps he takes here are a little convoluted and not necessarily something you'd be able to come up on your own. So I'm really just going to not justify a lot of these steps and say that this is what Griffiths says to do, so we're going to do it. We're going to define two terms. We're going to define a new variable z and define it as LA. And we're going to find a constant, z naught, defined as a divided by h bar times square root of 2m v naught. And immediately, I'm going to redefine all of the L terms here in terms of z. So what this is going to give me is that k is equal to z over a times tangent of z. Or alternatively, I can move the a over and I can get ka is equal to z tangent of z. So the ultimate goal here is to define everything in terms of one variable. In this case, I'm trying to get everything in terms of z, because if I can get everything in terms of a single variable, then I can plug this into Desmos, and then I can just find what z actually is, and then plug that into the relation between z and L, and then replace L with the actual relation of e and v naught. So that is sort of easier to do than sort of having all of these implicit dependencies via k and L. So our task now is sort of to redefine Ka in terms of z and z naught. So to do that, this is where the more convoluted step comes in. I'm going to take k squared plus L squared. Because I have k and L here, they're both square roots. So it sort of almost seems to suggest that maybe I should take their sums squared, because also, especially considering that they share a denominator. So this is negative 2me over h bar squared plus 2me plus 2m v naught over h bar squared. If we add these together, this just becomes 2m v naught over h bar squared. Once again, seems like this sort of came out of nowhere, and I wouldn't blame you for being thrown off by just this sudden step of taking the sum of the squares. but it ultimately the math works, so we're just going to follow his general idea. So we have k squared plus L squared is equal to 2m v naught over h bar. If I isolate k here, then k is actually equal to the square root of 2m v naught over h bar minus L squared. And if I multiply an a in front, then ka is actually going to equal square root of, let's see, this is going to be 2m v naught a squared over h bar. Is that correct? No, this is, apologies, this is h bar squared. So a squared over h bar squared minus la squared. And at this point, immediately we see an la here. This can be substituted with z. And we also see z naught is a over h bar times square root of 2m v naught. So z naught squared is just this term squared. So ka is going to equal z naught squared minus z squared. So if we plug this back in, then what we have is that the square root of z naught squared minus z squared is equal to z tangent of z. And we can move this z over to the left, and we get tangent of z is equal to the square root of z naught over z squared minus 1. And this actually sort of is an equation that we can sort of solve relatively easily via computers. We can just plug this into Desmos, get valid values for z, and then after that plug that into the fact that z equals LA, plug in the resultant form for LA, and then get E that way. So this is kind of it. We've finished this problem. This is a transcendental equation for z, and hence for h as a function of z naught, which is a measure of the size of the well. So the next step sort of is to look at limiting case scenarios, because we have this transcendental equation that is possibly a solution, but it doesn't really tell us that much. And oftentimes when you arrive at an answer, what you do is you take the limiting case scenario of extreme values of certain variables, and you see sort of if the resulting sort of answer that you get makes sense or not. So that's what we're going to do next, is we're going to do a sanity check by looking at limiting case scenarios. Okay, let's look at the first edge case. So obviously z is a constant. So I mean z is a variable, so we can't vary. We can't change this into any limiting case. But z naught is a constant, so we can start looking at the edge cases of z naught being either 0 or infinity. So let's look at edge case 1, which is also known as a wide deep well. Because what'll happen is that, well, if we look at z naught, the constants that can be altered, h bar is a universal constant. It can't be changed no matter what. Same thing with m, that's intrinsic to like the particle. But the things we can change are a and v naught. So a is the width of our well, and then v naught is the depth of our well. So if either of these becomes very big, then we have a wide well or a deep well, or we have a well that's both, in the case where both a and v naught are really big. So in all three cases, z naught goes to infinity. So let's suppose that tangent of z, so limit as z approaches infinity of tangent of z equals square root of z naught over z squared minus 1 as z naught approaches infinity of this whole thing. So in that case, then what we get is that tangent of z equals, this goes to infinity, square root of infinity is still infinity, so this is just infinity. The answer for this is then z is equal to n pi over 2, because if you graphed tangent, it looks, you know, something like this, I believe. And when it diverges to positive infinity, these are multiples of pi over 2. Equals n pi over 2, and n specifically is odd. So at z equals pi over 2, at z equals 3 pi over 2, at z pi equals 5 pi over 2, those are all the values at which tangent of z diverges to positive infinity. So if we look at this now, we know then that z is equal to n pi over 2 in the edge case where we have an infinitely wide, infinitely deep well. So we know that z is equal to LA, and we also know that L is equal to the square root of 2m of E plus V naught, all divided by h bar. So what we can say is then that A times square root of 2m E plus V naught divided by H bar is equal to N pi over 2, or square root of 2m E plus V naught is equal to N pi H bar over 2a, or 2m E plus V naught is equal to N squared pi squared H bar squared over 4a squared. And then move the other stuff over, and what we have is E plus V naught is roughly equal, because remember this is the limiting case where we're going to infinity, not exactly at infinity, N squared pi squared H bar squared over 8ma squared. And this is promising because the reason why this is promising is because for an infinite well, way back at the start of this chapter, we introduced the infinite square well. We saw that the energy levels for the infinite square well were equal to N squared pi squared H bar squared over 2ma squared. And we can rewrite this as N squared pi squared H bar squared over 2m times 2a squared. So in this case, a squared, a is the width of the well. Where if we have like a well, you know, this is equivalent to a. Here we have the exact same scenario, but we're just using different notation where half of the width of the well is equal to a, so the entire width is equal to 2a. So in a way, these two are effectively identical. It's just that the notation for a is different. The a here represents something different compared to the a here. A here is the full width, and then a here is the half width. So 2a is actually the full width of the well. So what we see is that in the case of sort of our finite well becoming infinitely deep and infinitely wide, the solutions for energy sort of approach the infinite well solutions. And that's promising because that's what we expect, you know, is if our well gets infinitely deep, then it just becomes an infinite well. If our well becomes infinitely wide, same thing. So that's promising. And next, we're going to look at the case of an extremely shallow, narrow well, where sort of we start approaching what looks more like a delta function. One additional thing I actually forgot to mention is the fact that remember that the indexes we have here are n equals 1, 3, 5, comma, comma, comma. So we don't actually have every single energy for the infinite square well. We actually have exactly half of them with the odd indexes. And what would happen is if we had assumed that psi of x was odd instead and used d sine Lx, then what we would have gotten was the exact same energy setup in this limiting case, but with n indexes being even instead of odd. So what happens is that the set of solutions where psi is odd instead of even gives us the remaining half of the valid solutions for the limiting case of a wide deep well. And more generally, the odd solutions of psi give us half of the valid energies, and the even solutions of psi give us the other half of the valid energies. Okay, now in the second case, where we go the opposite way and make z naught go to 0, this represents a narrow, shallow well, either narrow, either shallow, or both, because if we look at what z naught equals, if we want it to go to 0, the only things we can vary are a and v naught, which are the width of the well and the depth of the well. So if both go to 0, then it's a very narrow, shallow well. And in a case like this, unfortunately, this doesn't necessarily, like, if z naught goes to 0, then tangent of z goes to just the square root of 0 minus 1. So this doesn't really tell us anything because this suggests that tangent of z has to have an imaginary result, which obviously doesn't really make sense. So because of that, unfortunately, sort of trying to work this out mathematically doesn't really tell us that much. If we were to graph this, though, then what we'll see is that as z naught sort of gradually approaches 0, the number of solutions that are valid for valid energy levels effectively slowly gets smaller. And the reason why that happens is because if we have a well, then we have, so this is like negative V naught. And what will happen is that, like, we have a number of valid energies denoted by the index n. So as n gets larger, the energy level gets higher. So we have, we have some base energy, E naught, and then we have some like higher energy, E1, and then E2, and then E3, and so on and so on. After a certain point, if E gets too large, if E naught eventually gets so large that it becomes positive, then it's going to become a scattering state. So there is a finite number of energy levels that can fit in this well. And if it gets too large and it becomes positive, then it's not going to be a bound state anymore. It's going to be a scattering state. So what happens is if we make this well super narrow, then the number of energy states that can actually fit in here, because each energy state is separated by an index n, each energy state is effectively equally separated from each other. As this well gets really, really narrow, the number of energy states we can actually have gets smaller and smaller. And after a certain point, like, just like the higher energy states all disappear, because if you had energy states at that level with this shallow of a well, those wouldn't be bound states anymore. They would be, they would be scattering states. If I had a well that was like, only this big, if it only went up here, then only this state would be valid, because like it's not necessarily, it doesn't make sense for an energy to be more negative than the bottom of the well. So all of these would vanish. And effectively, what will happen is that as Z naught gets smaller and smaller, the number of valid energy values, aka the number of valid solutions for Z, also gets smaller, until a certain point where, if you graph this out mathematically, you'll see that if Z naught becomes less than pi half, then after this point, there's only one valid solution for Z. So you can graph this out for yourself if you want. Just graph out this transcendental that we have here, and what you'll see is that as Z naught gets smaller, the number of valid Z solutions also gets smaller, until a certain cutoff point exactly at Z naught equals pi half, after which there's only ever going to be one valid solution. Now, interestingly enough, there's always going to be at least one bound state. As long as Z naught doesn't go to zero completely, in which case the well just straight up disappears, there's always going to be a valid solution, no matter how quote-unquote weak this well actually is. So that's just a very interesting point. But other than that, there really isn't that much to analyze in the case of the very narrow, shallow well. And also, this also makes sense in a limiting case. As this well gradually gets smaller, in the limiting case where it disappears, there aren't any valid bound state solutions at all, because now there's no longer sort of a well that's maintaining bound states. So we've seen, therefore, that in both limiting cases, the resulting answer we get makes sense. So therefore, we can be reasonably confident that this result that we've gotten is, in fact, a correct result. So now that we're done with treating the bound states, we can move on to looking at the scattering states. Okay, there's a bit of subtlety to scattering states when we're looking at a finite well that isn't really present when we're looking at bound states. So I'm going to draw this out first. So for a scattering state, we have our finite potential well. Whoops. Yeah, okay, we have our finite potential well with x equals negative a here and x equals positive a here. And our well, something like this. So what is going to happen? So traditionally, in classical mechanics, if I had, say, for example, just a ball rolling this way, the ball has some energy, and if the ball has more energy than sort of the potential dip of this well, it's going to, and in classical, obviously, also this wouldn't be a straight well. It would be a hill, right? Look something like this. If the ball has more energy than sort of the dip in this hill, if the ball has more energy than like the gravitational potential energy change as you dip down, then it's going to be able to make it all the way through to the top, to the other side, effectively. In quantum, since everything is based on probability, what's going to happen is you're going to have sort of a particle. It's going to be a free particle traveling, this way. There's going to be some sort of barrier here, and the particle is going to have a probability of either getting reflected back or it's going to make it through, exactly just like in the case of an infinite delta well. Then this is effectively just two delta wells, sort of. So the particle is going to the right again. It's going to have a probability of getting reflected back, and then there's also a probability that it transmits all the way through again. So if we look at this, and also if we sort of think back to what the Schrodinger equation is going to look like, it's effectively exactly the same. In the region with v equal to 0, our Schrodinger equation looks like negative h bar squared over 2m d2 psi by dx squared being equal to e times psi. And then in the region with v equals negative v naught, we have negative h bar squared over 2m d2 psi by dx squared minus v naught times psi being equal to e times psi. So this setup is effectively exactly identical to the case of the bound states. If you look back on the video to the section when we just start talking about bound states, the Schrodinger equation setup is the exact same. The only difference now is that the sign on energy changes. So because of that, we going to have to say that, like, d2 psi by dx squared equals negative k squared psi, and then this one's going to be like d2 psi by dx squared is equal to negative L squared psi. In fact, this one is actually unchanged, because if we remember, L is actually equal to square root of 2m times E plus V naught over h bar. And in this case, regardless of whether or not we have a bound or scattered state, in the scattered state, E is just always positive anyway, so this is just straight up going to be positive no matter what. We can't absorb the negative into the square root. So, and then in the case of the bound states, even though E is negative, it can never, sort of the magnitude of E can never surpass V naught. So because of that, this is still always going to be positive. So because of that, the region with V being negative V naught has the exact same setup as in the bound system. And in the region with V not being finite, or not being non-zero, with V just equaling 0, the difference is that now we have to pull the negative out of the square root and make it negative k squared psi. So what we're going to result in is it's going to be a piecewise function as before of a times e to the ikx plus b times e to the negative ikx when x is less than negative a. So this represents the two waves, one coming in, one coming back. In the middle, we have, so the thing here is that you would expect psi to behave exactly like this. You would expect it to be a complex exponential because we're dealing with a scattered state. However, so what we would expect is something like ce to the ikx plus de to the negative ikx. This is what we would expect for this middle region. The thing is, this system has two valid solutions, right? One of them is the complex exponential, a e to the ikx plus b e to the negative ikx, and the other one is the sinusoid, a sine of kx. Actually, it shouldn't be kx, it's lx. Apologies. Lx, Lx, and then this bottom one is also sine Lx plus b cosine Lx. So these are both valid solutions. The thing is, this represents a free particle. Traditionally, we use complex exponentials to define free particles which are not under the influence of any potential. So when v is equal to 0, this complex exponential is the right way to go. In this case, even though it still technically is even though it's still like a moving wave, it's not necessarily a free particle. Like, the fact that in this middle region there is a non-zero potential at v equals negative v naught, this implies that it's not necessarily valid anymore to treat the particle in this region as a free particle, because it isn't quote unquote free. It's under the influence of a potential. So because of that, we can no longer use complex exponentials to define the wave function. Like, we technically could, but it would result in problems later down the line. So in this middle region, it would be more appropriate to write it in terms of a sinusoid. So the correct writing is instead c sine Lx plus d cosine Lx. And then finally, in the outer region, over here, we have e times e to the ikx plus f e to the negative ikx. So this is now our new piecewise function. So this is from negative a less than x to positive a, and this is when x is greater than a. So our piecewise function has two complex exponentials in the region where v is 0, and then we have a general sinusoid in the region right in the middle. And next, we're going to do the same thing we did in delta well, which is we're assuming that our incident particle comes in from the left. So it doesn't make sense to have sort of fe to the negative ikx, because if we're assuming that the particle comes in from the left, we're never going to have the particle come in from the right. So for the same reason that we get rid of the e to the negative ikx term on the right for the delta well, we're getting rid of it here as well. Now, next, this is basically the same thing as before. We introduce sort of all of the boundary conditions of the continuity via psi and d psi by dx, and then we can find, you know, reflection coefficients and transmission coefficients. So as an example, let's try to find the transmission coefficient of this system. So let's apply boundary conditions. So we have the continuity of psi, which is going to be, so let's see, continuity at x equals negative a. This is going to be a e to the negative ika plus b e to the positive ika must be equal to c times sine of negative la plus d cosine of negative la. Sine is an odd function, so we can get rid of the negative here and move it to the front. And then d is an even function, so the negative just doesn't matter. So this is our real continuity equation. Then we want the continuity of derivative at x equals negative a. This is going to be, let's see, ik at the front multiplied by negative a e to the negative ika. No, wait, that's not quite right. Hang on. I'm just, instead of trying to do this right away instantly, let's see. Ik, and then a e to the negative ika minus b e to the ika. And this is equal to L and then c times cosine of LA plus d times sine of LA. That should be correct, right? Because the negative at the front becomes a positive. Yes. Okay. Yeah. And then we also have the continuity at x equals positive a. Which is going to give us that c sine LA plus d cosine LA is equal to e times e to the ika. And then we have the continuity of derivative, which is going to be L times c cosine of LA, and then minus d sine LA. This is equal to ik e times e to the ika. And then at this point, it's just a matter of sort of getting all of these, combining all of these together and sort of solving the system of equations in order to find the transmission coefficient. I'm not going to bother doing that. We've done that plenty of times already in the previous problems with the delta well. I'm just going to write out what the final coefficient is. So the transmission coefficient finally is just going to equal like the magnitude of f squared divided by the magnitude of a squared. And it's just, it's going to turn out that the inverse of the transmission coefficient is going to be equal to 1 plus v naught squared over 4e times e plus v naught times sine squared 2a over h bar square root of 2m e plus v naught. Once again, it's not too important to be able to solve this by hand. I would heavily recommend you just plug these equations into Mathematica and have it solve the system for you in order to get these transmission coefficients and reflection coefficients similarly. Now, interestingly enough, there is a point of interest here, and it's that this, t inverse becomes equal to 1, which is just equal to t, when the sine argument becomes 0. So when 2a over h bar times square root of 2m times e plus v naught is equal to 0. Or not equal to 0, it's when it's equal to, when sine of x is equal to 0, x has to equal n pi. Yeah, so when this equals n pi, with n equaling like 1, 2, 3, so on and so on. So this is coming directly from this term right here. The fact that, like, if the sine term is 0, then this entire term is 0. Then the inverse transmission coefficient is just 1, which means that there's a perfect 100% chance of the particle making it through the well. So this is interesting because what it sort of suggests is that there's very specific energy levels for which, when a particle has those energy levels, it somehow sort of resonates with the entire system. Resonate's not really a good word, but there's something special about those energy levels, specific energy levels, that allow the particle to just have a 100% chance of moving through the well, as if the well wasn't even there in the first place. So if we look at this, we can solve for E plus V naught, and what we get is that 2m E plus V naught is going to equal h bar over 2a times n pi squared, or 2m E plus V naught is equal to n squared pi squared h bar squared over 2a squared, aka E plus V naught is equal to n squared pi squared h bar squared over 2m 2a squared. And if we look back up here, well, I think I might have deleted it, unfortunately, but this is exactly equal to the energies of the infinite square well. When we did the limiting case scenario for the bound state, where we had an infinitely wide and infinitely deep well, the resulting energies we got was exactly this. So it turns out that when the energies are the energy exact, when the energy of the free particle is exactly equal to the energies allowed for the infinite free well, the particle can just somehow travel through the it can just travel through the well as if there wasn't any well at all. And this is very obviously not something that we expect from classical mechanics, because in classical mechanics what we expect is that, you know, the particle either is able to make it through the barrier or it isn't, and there's a cutoff point in the energy for which, if it has energy less than this cutoff point, it's not going to make it through the dip. And if it does have energy above this cutoff point, it is going to be able to make it through the dip. So in quantum mechanics, apparently, because of the fact that, you know, probability is very weird and there's all of these weird sinusoid interactions, there is evidently sort of, apparently, an oscillating probability for the particle to either make it through or not make it through the well, or at least be more likely to make it through the well. And at specific points that are exactly equal to sort of the separation in the energy levels of an infinite square well, at these energy levels, the particle has a perfect chance of making it through the well. If we graph the transmission probability with respect to the energy, we would get something like this, where these energies right here, these energy levels for which correspond exactly to the infinite square well energy. So this is like, you know, pi squared h bar squared over 2m 2a squared, and then like this one is like 2 pi h bar squared over 2m times 2a squared, and then this one's 3 pi h bar squared, and so on and so on and so on. So it's a very interesting phenomenon to observe, and once again it sort of hammers home the fact that you know, quantum mechanics and classical mechanics don't really play on the same set of rules. And with that, we are done with Chapter 2, and after finishing all the remaining problems on Chapter 2, we can move on to Chapter 3, which involves formalism, and finally introducing linear algebra, which is sort of technically considered the true language of quantum mechanics. Apologies, I've made yet another error. I was following the Griffiths textbook here. This, for our case, is supposed to be the magnitude of e squared, because our sort of term here is e. The term that actually represents the particle making it through the well is big E. So it's actually magnitude big E squared over magnitude big A squared. And another big thing to note is that the E here, you know, the three E terms here are not equivalent to the magnitude E squared here. This is the coefficient in front of sort of the complex exponential that represents amplitude of the wave function. These E's are actually energies. So these are the energies that come from redefining K and L after we finish finding the transmission coefficient. So yeah, just to clear that up, apologies.